Good day to you and welcome to our class. Today we shall be talking on Laplacian sum of derivative. Now, we are talking about Laplacian sum of dy dt, that is derivative, or let's say Laplacian sum of second derivative, like that. Now, let's start with the first derivative, dy dt, or we say dy dx, but we are dealing with t now. Now, if we go by definition of Laplacian sum, this is 0 to infinity exponential minus st then dy dt. So this is Laplace transform of derivative. Now we can simplify this thing further by using integration by part. Now, how do we apply the integration by part? So, we first say that let u be exponential minus st and let the v be dy dt, that is this one. From this place, if you differentiate the u, if you differentiate this, we have minus s exponential minus t dt. Also, to find our v here, we integrate, and this is differentiation already. When we integrate this differentiation, it will become y. So, or let's just say y of t. So it will become y of t, or simply y. If you recall the formula for integration by part, it says u dv is equal to uv minus integral v du. So in that case, our Laplacian sum of dy dt will now be equal to, we use this uv, this is our uv, that is y of t exponential minus t. Here I'll put the boundary 0 to infinity, followed by minus integral 0 to infinity. This is the formula we are following, minus v, this is our v, du dt, that is y of t, this is our v, this is our du dt, times minus s exponential minus st dt. Let's come to this place. If you put t to be infinity, you are going to have exponential minus infinity. This will be y. Let's put t to be infinity. This is y of infinity, exponential minus infinity. Let's put t to be 0. Then that will be we say minus when t is 0. This is y of 0, exponential 0, followed by minus. This minus will make this place to be plus. So we should now have s is constant there, so we can bring it out. Let's say s is here, 0 to infinity. I'm rearranging this now, exponential minus t times this y of t dt. So from that place, we have that Laplacian sum of dy dt will be equal to, this one will be 0. This one will be minus y of 0. Exponential 0 is 1. So we don't know y of 0. This y of 0, we call it an initial condition. Then plus s. If you look at this, this is just definition of Laplacian sum. So this is Laplacian sum of y. So what we are now saying is that Laplacian sum of dy dt is s Laplacian sum of y minus y naught. So that is our answer. So we should take note of that. So this y naught is the initial condition it will be given. Now let's consider Laplacian sum of second derivative. So this is the one we prove down. So, and it is the one we are going to use for this one. Since Laplacian sum of dy dt is s ly and y naught of 0. From this place, we can say that this, for the second derivative, this will become SL again, but first derivative now. Instead, as this one is ordinary y of t, it will be, as this one is y of 0, it will be dy dt of 0, which this one, we just write it as, this is how we write it, y prime of 0. That's how we write it, instead of ordinary y. Now, s Laplace transform of dy dt is this. Let's put it there. This will be s Laplace transform of y minus y naught. So minus this one is y prime of 0. So from that place, this will give me s squared Laplace transform of y minus, this is s y naught minus y prime of 0. Similarly, when we find the third one, we should be able to have s cubed Laplace transform of y minus s squared y naught minus s y prime naught minus, this will be minus y prime prime naught. But the ones we are considering are just the first two derivatives. They are this. The first two derivatives, I've written out this one. I'm writing out this. We need to memorize these two. They are very, very important. Now let's take an example on this. For example, find the Laplace transform of this differential equation. This is a differential equation. Given that y naught is 0, y prime naught is 0. So they will be given y naught, y prime naught. All these are initial conditions. They will be given to us. Now, the first thing is that we take the Laplace transform of both sides. That is, we find the Laplace transform. That is, we put L to everything, to every expression here, and that will becomes this. That's our first step. The second step now is we need to substitute the value, the expression for this Laplace transform of second derivative and Laplace transform of this first derivative, as in these two. We need to substitute. When we substitute them, we are going to have this. This is the Laplace transform of second derivative. It started from this place and ends here. Plus, this is our 5. The 5 is here. Laplace transform of this first derivative is put in this bracket. This is our 6. Laplace transform of y is there. Laplace transform of 0 is 0. From these two, we need to memorize these two. Now, after we have done this, the next step is that we substitute these values into this expression. Anywhere we see this expression, we substitute this value. Now, this will become s squared L of y minus s y naught is 0. We put it there. Minus y prime naught. Our y prime naught is 1 plus 5. If you have this, we have 5 s L of y minus y naught. Our y naught is 0. And this has no anything there. We leave it like that, is equal to 0. After that, we need to simplify. Expand. If you have bracket there, we expand it. This is s squared Laplace transform of y. This one is not useful. Minus this one. Plus, if you expand this, we have plus 5L Laplace transform of y plus 6 Laplace transform of y is equal to 0. Our aim is to find the Laplace transform of y. So anything involving Laplace transform of y, okay, there's L here, we pack them to one side. So let's factorize everything involving Laplace transform of y. This one involves, we have s squared. This one involves, we have plus 5s there. This is plus 5s. And this one involves 2, we have plus 6. Then Laplace transform of y. The one without Laplace transform of y, we take it to the other side. This is minus 1. When we take it to the other side, we have plus 1. Now, our aim is to find Laplace transform of y. And our answer will be equal to 1 divided by s squared plus 5s plus 6. So, that is our answer. We have successfully found the Laplace transform of this differential equation given this. So this is the Laplace transform of y. Now let's take another example. Second one, find the Laplace transform of this equation. This is a differential equation. Given that y naught is 1 and y prime naught is 2. So, solution. The first thing is we take the Laplace transform of both sides. This, and this. Now let's put Laplace on. Let's put L to both sides so that we have this. That's the first step. We put L to both sides. That is, we take the Laplace transform of both sides. After, we now need to substitute these two expressions. Where we see this, we write this. Where we see this one, we write this one. And we can see them here. Now, when we write them, we are going to have. Now, when we now find this, it gives me the whole of this. Plus this is our 2. Laplace transform of the y dt is there in the bracket here. And finally, this is minus 8 Laplace transform of y equal to Laplace transform of exponential t. We know that Laplace transform of exponential t is 1 over s minus 1. After this, we need to substitute these values. Y naught is 1 and y prime is 2. So this will give me s squared Laplace transform of y minus y naught is 1. This is 1. This one is 2 plus 2 into s Laplace transform of y. Y naught is 1. This is minus 8 Laplace transform of y equal to 1 over s minus 1. From this place, we just need to expand or simplify. This is minus s. This will give me minus 2. If you expand this, we have plus 2l, 2s Laplace transform of y, 2 times minus 1, that is minus 2, minus 8 Laplace transform of y equal to 1 over s minus 1. So that is what we are going to have. From this place, anything with Laplace transform of y, you pack them together. Starting from this is s squared. This is another one, plus 2s. This is another one here, minus 8. Then we put Laplace transform of y. Our aim is to find this. Now, anyone without Laplace transform of y, let's put them to the other side. This is minus s. When it comes here, it becomes plus s. This is minus 2, minus 2. That will become minus 4. When the minus 4 comes here, it becomes plus 4. Let's see over 1. We can find the LCM. So this one still gives me s squared plus 2s minus 8 Laplace transform of y equal to, we find the LCM here. LCM is s minus 1. Just cross multiply. This is 1 plus s minus 1, s plus 4. So we still continue this. We find the LCM. When we simplify this top one, we should be able to have s squared plus 3s minus 3. When we simplify this top one, so we should be able to have s squared plus 3s. Then, this is minus 4. Minus 4 plus 1, that will be minus 3. Now, our aim is now to find the Laplace transform of y. If we find the Laplace transform of y, we are now going to have s squared plus 3s minus 3 divided by this s minus 1. When this one comes to the other side, it will become s squared plus 2s minus 8. So that is our answer. So this is the Laplacian sum of this derivative. We have successfully found the Laplacian sum of this dy ds, this differential equation. The beauty of Laplacian sum is that we can find the solution of this differential equation. How do we do it? We only need to find the inverse transform of this. And I've taught you how to find the inverse transform. We use partial fraction. We have done that in our last videos. So we can find it. That is one of the applications of Laplace transform. And that will lead us to application of Laplace transform. Application of Laplace transform to the solution of differential equation. Step 1, we find the Laplace transform of the given differential equation. Just like this. As we want to find the solution of this differential equation, our first step is we find the Laplace transform, which is this. That's the first step. The second step is that we now find the inverse transform. So let's take this as an example. Example 1. Look at the way the question will come. Solve this equation by Laplace transform. You can see we want to solve this equation by Laplace. It's different from how we wrote the question here. This one says find the Laplace transform. This one says solve this by Laplace transform. Given that y naught is 1 and y prime naught is 2, it's just the same thing. So the first step is that we first find the Laplace transform. And thank God, we have found the Laplace transform to be s squared plus 3s minus 3 divided by s minus 1 s squared plus 2s minus 8. That's what we got. So this is our first step. The second step now is that we find the value of y by taking the inverse transform. We find it because when we take this L to the other side, it will become inverse transform of L. So that is this over s minus 1 s squared plus 2s minus 8. This is inverse transform by partial fraction. You need to go and learn the partial fraction in any ways. You need to go and learn. I don't need to be writing this. Before we apply partial fraction, we first take note of this, whether it can be factorized or not. So the way I'm looking at it can be factorized. When we factorize it, we should be able to. It should be s minus 2 and s plus 4. So we'll come back to this place. This is where partial fraction comes in. S squared plus 3s minus 3 over s minus 1 s minus 2 s plus 4. We say a over s minus 1 plus b over s minus 2 plus c over s plus 4. So I don't need to be doing all this, but I'll just use this as an example. In our subsequent example, I'll just move straight to the point. Now, let's use cover-up rule to find the value of a. Our value of a is s squared plus 3s minus 3 divided by, you cover what is under this a. This is what is under a. You write the remaining two expressions here. These two, you write them. That is s minus 2, s plus 4. So you now need to remember from this list, s will be equal to 1. Here, s will be equal to 2 when we equate it to 0. Here, s will be equal to minus 4 when we equate it to 0. From that place, we are finding the value of a. We substitute a to be s to be 1. Anywhere we see s, we put it as 1. This will be 1 square plus 3 into 1 minus 3 divided by 1 minus 2, 1 plus 4. 3 minus 3 is gone. 1 minus 2 is minus 1. So our answer here should be minus 1 over 5. So we have found the value of our A to be minus 1 over 5. Now let's find the value of our B. We follow the same process. B is s squared plus 3s minus 3 divided by, we cover up what is under B. We write the remaining two, s minus 1 and s plus 4. S minus 1, s plus 4. Now, we put s to be, what we got under B is 2. We put s to be 2. Anywhere we see s, we put it as 2. S is equal to 2. So this will become 2 squared plus 3 into 2 minus 3 divided by 2 minus 1, 2 plus 4. Now, this will give me 4 plus 10 plus 6, that is 10. 10 minus this, that will be 7. 7 divided by 2 minus 1 is 1. 2 plus 4 is 6. So we have 7 over 6. That's our B. So we now need to find our C. Still the same process. S squared plus 3s minus 3. We cover up what is under C now. We write these two. That is s minus 1, s minus 2. Then we put s to be minus 4 this time around. S is equal to minus 4. So this will be minus 4 squared plus 3 into minus 4 minus 3 divided by, this will give me minus 4 minus 1 minus 4 minus 2. Now our answer here is 16 minus 12 minus 3 over, this will give me minus 5 minus 6. 16 minus this is 4. 4 minus 1 is 1. Minus 5 times minus 6 is 30. So C is 1 over 30. Therefore, our Y will now be inverse transform of, this is what we are now going to follow, these 3. We just need to put the value of A, B, C there. Our A is minus 1 over 5. Minus 1 over 5 divided by, what we have there is s minus 1. Plus our B is 7 over 6. This is our B here. This is B over s minus 2. Plus C. Our C is 1 over 30. S plus 4. Finally, our answer is, it is easy to find the inverse Laplace transform of this. We have done that. This will give me exponential t. Plus, this one is 7 divided by 6. This will be exponential 2t because we have minus there. And 1 over 30, this will give me exponential minus 40. So that is our answer. So we have found the solution of this differential equation given this condition. So that is, we have used Laplace transform to find the solution. You can see it once again. So in our next video, which should be titled Laplace transform of derivative part 2, we are going to consider more examples there.